A satellite is an artificial body placed in orbit around the Earth or another planet. There are also natural satellites, such as the Earth or Moon. An orbit is the regularly repeated elliptical course of a celestial object or spacecraft about a star or planet. The general uses of a satellite include capturing pictures which are used to predict the weather, such as tracking hurricanes, capturing images of other planets, transmitting TV signals and phone calls, GPS made up of 20 satellites, and many more. Satellites are important for many reasons. Satellites allow for large areas of Earth to be seen at bird's eye view, so therefore they can collect more data more quickly than ground instruments. They also allow for signals. TV signals travel in straight lines, so they can trail off or be blocked by tall objects such as buildings or mountains. Instead, satellites can send signals back down to a different location after receiving them, allowing for TV broadcasting. Also, telephone wires over long distances are difficult and costly, so satellites allow for phone signals instead. The very first satellite was launched on October 4, 1957, called Sputnik. This was a Russian beach ball-sized space probe. This satellite was a pressurized sphere made of aluminium alloys, which were used to test orbital tracking, orbit lifetime, and the effects of radio wave propagation through the atmosphere. 1 month later, on November 2, 1957, Sputnik 2 was launched, which was a large... 1 month later, on November 7, 1957, Sputnik 2 was launched, which was a large Soviet satellite which carried a dog. The satellite was designed for a 7-day flight, however, unfortunately, Laika the dog died on its 4th orbit. On January 31, 1958, US Explorer satellite was launched, which measured the radiation environment and detected Van Allen radiation. December 18, 1958 marked the first communications satellite called SCORE, which sent a Christmas message from the President. It showed that satellites could receive and retransmit signals from one location to another through using orbital relay equipment. The next development in satellites came in 1960 with the launch of TIROS, TV Infrared Observation Satellite. This was a meteorological satellite which was launched to test the feasibility of using TV cameras to observe the Earth's cloud cover. This sparked a series of satellites used to create a worldwide weather satellite system to provide accurate weather information. Later in the year, on August 12th, Echo 1A was launched, which was a balloon-shaped satellite made of mylar polyester film. It was used as a passive reflector of microwave signals through using beacon transmitters. These transmitters were powered by nickel-cadmium batteries charged by solar cells. The world's first active communications satellite was called Telestar 1, launched on July 10, 1962, in low Earth orbit with an orbit time of 2.5 hours. It allowed for television programs to be broadcasted across the Atlantic and for calls, signals, and images to be sent through space. This enabled long-distance phone calls and real-time TV. August 19, 1964 marked the first geostationary satellite, SYNCOM-3. It provided live Olympic game coverage from Tokyo and had an elliptical orbit. On December 7, 1966, ATS-1, Applications Technology Satellite, was launched as the first experimental equatorial synchronous satellite used for transmitting weather images at a geostationary orbit. In 1970, Uhuru, also known as the Small Astronomical Satellite, was launched and entirely dedicated for celestial X-ray astronomy. The X-ray sources allowed for detection of binaries, supernova remnants, and many galaxies. The satellite also led to the discovery of the diffuse X-ray emission from clusters of galaxies. In 1974 and 1975, communication satellites were more developed, with first WESTAR launched in geosynchronous orbit, which relayed data, video, and fax transmissions. Then RCA SATCOM was launched, which initially was used for voice and data, but later was utilized for major use in broadcasting TV. The final big development was in 1976 with the launch of Marisat for maritime communications. This satellite connected with the sea in relation to navigation and shipping. This allowed for dependable communications for commercial shipping. It was placed in geosynchronous orbit. As you can see from the timeline of satellites, there are many different types of satellites. One type of satellite is a weather satellite. Weather satellites, such as Meteosat, continuously monitor weather on Earth using radiometers, then transmit this data to Earth. This can include sea temperatures and depths, radiation from Earth's atmosphere, and deforestation, amongst other things. In geostationary orbit, the satellite orbits at around 36,000 kilometers above the Earth and orbit at the rate of the Earth's turn, so the satellites remain stationary relative to one point on Earth. They each monitor a single region over a period of time. Due to their high altitude, in order to image the Earth at a suitably high resolution, the satellites require precise scanning mechanisms and telescopes. In polar orbit, the satellites orbit at around 800 kilometers above the Earth and orbit in a path following the Earth's meridian lines, passing over the north and south poles with each revolution. Images are pieced together to produce a larger picture. Another type of satellite is the navigation satellite. Navigation satellites, such as Navstar Global Positioning System satellites, use trilateration to determine locations. A receiving device on Earth collects data from multiple satellites that include the position of each satellite and the time it took for the signal to reach the receiver. From this, the radial distance from each satellite is found, and the position of the receiver is where these circles intersect. Another type of satellite is the communication satellite. Communication satellites, such as Anik, are used to communicate radio, telephone, and television transmissions between separate points on Earth. An Earth station will transmit a signal, which is received by a satellite and retransmitted to another satellite or Earth station. The satellite transmitted from the Earth station is the uplink, and the satellite received by the Earth station is the downlink. Satellites are either passive and just return signals, or they can carry transponders, which will amplify the signal before retransmitting it. Usually, communication satellites are in geostationary orbit at around 36,000 kilometers. Sometimes they are placed in elliptical orbits with the Earth at the smaller end, so for the majority of the orbit, the satellite is above the region of the Earth it receives signals from. This region is called its footprint. A deeper analysis into satellite technology innovation is mainly focused on updated satellite types and generated material application. In the future, it is desirable to launch as many satellites as possible at once, so lightweight, simple structures, long life duration, and sensitive monitoring are important. One of the most basic satellite innovation techniques is to change the rigid body into an inflection body. This decreases the volume and weight of the satellites, so they can be formed into any shape. The speed of the structure forming can be controlled by the gas transfer feedback system. There are three main typical satellites: the inflatable satellite bus, inflatable signal receiving satellite, and the inflectable satellite antenna. Here is the inflatable satellite, which is used as a space travel machine. On the left-hand side is a 3D view of inflatable satellite bus. This satellite includes three parts: the solar power source, the inflatable body, and the central loading cabin. If we made a half-section view of the bus, the inflatable material covers the whole loading cabin, and the gas bag is at the bottom of the satellite, so high-pressure airflow will form up the shape immediately. The corner material is supported by a high-stiffness material to prevent shape deformation. Inside each assembly unit is the gas transform system. These gas support units have the same distance to each other, guaranteeing that the inflation time of each node is the same. Also, the gas system has a pressure feedback unit to control the internal pressure without exceeding the limit shape. This is a low-pressure inflatable process, aimed to keep the sensitive shape to deliver the signal to the central loading cabin. This type of satellite has an extremely small volume, so can be sent to space with large quantities at the same time. Also, being lightweight and multitasking is advantageous because of its simple system forming. This kind of satellite is a popular commercial satellite at present. This is the general structure of the cube satellite. The upper, middle, and base separately form a simple cube unit shown in the middle picture. The upper level usually contains different radiators and locking bolts for system stability. The middle and base structures are the central controlling units of the satellite. The bottom structure is called the MEMS structure and provides the solar energy, and when the MEMS structure is collapsing, the maximum primary static axial stiffness will reach 4170 megapascals. This is a testing table to monitor the stability of cube satellite rigid shell. Function 1 and 2 are the safety and deformation limit functions. This is it moving to the assembled base structure with low density and deform limitation sensitive layers. From FE analysis, in the deeper base, a higher stress will be obtained. So for the functions 3 and 4, they show the allowable deformation magnitude and the safety constant in each base. In the application of materials in new satellites, resin materials in polymer molecular forming methods conclude all the advanced materials in aerospace, the composites, metallic combination, and high-strength fibre structures. Here is the resin polymer materials. Against the normal resin materials, this advanced resin polymer will additively cover the layers of antioxidant, provide temperature control, and has anti-leakage film properties. It will need 6 to 8 layers, whereas the normal resin material only needs 4 layers. The resin material almost becomes a covering or sealing material in the satellite due to its high elongation and high stiffness. You can see the PCB, printed circuit base, is mainly covered with this material as its base support. Here is a multi-materials comparison. Next, we can define and discover the curing materials. This material is a new advanced UV curing material. This material reacts with ultraviolet rays, which activates the radical cations in the composite product so that the free radicals can combine with the high polymer to form a solid hard product, forming a hardened film on the attached surface. A low thermal coefficient material with a high stiffness is glass. The glass is made tough through the crystallization process to reach a better performance. The left-hand side image shows the previous material application chart. A separate structure diagram made in 2017 clearly proves the glass membrane is included in the layers of the MEMS thruster. Although the innovation of the satellites at present is aimed at reaching a lightweight and multitasking level, there are further aspects that need to be developed. There are many considerations in the advancement of satellites. The first consideration in advancing satellites is having low-priced, highly available resources. Saving money and efficiency is a problem that every industry is facing. The most common solution is through changing materials and increasing the fuel efficiency. However, there are a number of other solutions to reduce the expense of satellite development. Saving space in every possible satellite part, such as reducing the space occupation and the price of small internal electrics, will greatly reduce overall expenditure. It is currently possible to pack the power of the first Intel computer chip into motes, which are the size of pieces of dust, which currently cost about 10p. However, continuing advances in MEMS, microelectric mechanical systems, are expected to push the price down below a penny sometime in the future. A 30cm long satellite called Sprites has recently been made successful and contains 200 even smaller satellites in it, packed with technology. As chips are made even smaller and more precise, there will be a reduction in the cost and an increase in the function of the satellite in the future. For satellites with a specific function, reducing time in development is more important than reducing cost. Outer space being a huge environment means the transmission of signals will take a lot of time, which is a problem for real-time control of satellites, especially those with large amounts of data. In the case of observing satellites, a recent idea is to install chips which enable satellites to process the information generated by sensors themselves, rather than send the data back to Earth. One of the ways to do this is through a growing technology called intelligent multitasking. This embedded intelligent technology would eliminate the need for a centralized data processing facility. Each sensor in the technology would carry a microcomputer and various communication abilities, which would provide collaborative signal processing capabilities and the function to make group decisions about which data to send. For navigation and weather satellites, higher clarity and higher frame real-time state feedback will be necessary for improving data results. Quality of data, such as resolution, is important, especially for satellites observing planets. The future development of high-tech cameras and sensors will bring us better results of satellite work. The most important part of future satellite development is to develop new functions over just optimization. Updated future satellites will be used in a variety of ways in scientific research. The European Space Agency has developed a satellite group called SWARM, designed to map the Earth's magnetic field with accuracy. The satellites will end up in 3 different orbits to give scientists a 3D view of the Earth's magnetic field and how it is changing. The development of satellites will benefit our everyday lives. For example, with satellite systems already installed in planes, the simplest tweak could have airlines subscribe to the most basic and fairly inexpensive service offered by satellite companies, which includes the transmission of the GPS coordinates at regular intervals. This will greatly reduce the rate of aircraft loss of connection if implemented. While satellite technology is relatively mature now, the use of it tends to be multifunctional, like the sprites mentioned above, which are equipped with advanced functions like memory, metal, and solar charging. With the continuous exploration of scientific research, more satellites with more operations, such as repairing spacecraft or transporting resources, may be created with the development of space technology.